So, welcome to the mock interviews. Thank you for participating. So today we're going to be doing, I think, probably about an hour session, 45 minutes or so, 45 to 50 minutes or so working time. Are you comfortable with controlling time, or do you want me to kind of help you on that front?
Sure, I can take a look at the time while I'm working on it. It's
Okay.
12 right now, so yeah.
Okay. So you can have a look at the time. We'll just get into the problems, and in the end, we'll do feedback instead of the regular interview stuff.
Yeah,
Okay.
sounds good.
Cool. So the first question, I would like you to implement a function called power.
Hmm.
And power is taking two parameters, a base, which is a float, and then a exponent, which is an integer. And you
Hmm.
are to return the base raised to the power, base raised to the exponent.
Okay. Hmm. There are already library functions that do this, but I'm thinking that we probably need to do
Yes,
it in the code.
that's right. That's right. We'll be implementing our own version.
Okay. Um, so the exponent can be positive or negative, right?
That's right. It can be positive or negative. It could be any integer.
Okay. Hmm. I think um I think quickly what I thought of from like a basic uh, understanding that I have is like for positive exponents we are just multiplying by the number by itself for whatever the exponent number of times, and for negatives we are doing uh, um, I think we're doing square root or if I'm not wrong. No, I think that's
Square
for
root is not
fractional.
quite. Yeah, that's right.
Yeah, that's fractional. Uh, for negative exponent, I'll just do for positive ones first. So x is 0. Then I'll just do in range. And then base equals base times base. And then base. That's for positive exponents. Um, but also you said they're integers, so there's no worry of doing a square root or anything. Um, the only thing is the negative exponents. I had a question because I don't know if it's leaving. What's 2 to the -1? Um, what should the result be?
So
Because
so the
I just want to be
definition
sure.
so definition of a negative uh,
Yeah,
exponent is x to
yeah.
the power of, let's say, negative. Let's use a. Let's use n. What do you use? Use e. No, I'll just use n.
Hmm.
Is going to be the equal to 1 divided by x to the power of positive n.
Right, right. Okay, okay, yeah, makes sense. Okay. Uh, okay. In that case, I mean, we can um, do the same thing for both positive and negatives. And if the exponent is negative, we can just return the 1 over the answer. So I can get the absolute value um, uh, and store it something like this. Uh, and then I'll do remove the loop, the condition, and then in range just be this, and then if the exponent is less than 0, turn 1 over um, absolute 1 over base. And then there, then um, something like this.
Okay. Can we go through an example?
Yeah. So if, uh, let's say if the base is 2 and the exponent is 3, we're doing 2 into 2 into 2, which is uh, 8. And the way that I have written this, like we iterate through the range between 0 and exponent, and then we for each iteration we multiply the base by itself. Um, and if the exponent is less than 0, then we return 1 over the base. Otherwise, we just return the calculated product. It should work for negative exponents as well. So 2 to the negative 3.
Mm-hmm.
It should just be 1 over 8 instead of 8.
Okay.
The only case I would think is like if for the 0 case,
Yep.
um, so 0, the anything raised to the 0 should be 1. So that could be like a really, if x equals 0, return 1. Uh, we should consider all these integers as the exponents.
Okay. And what if the base is 0?
If the base is 0, 0 raised to, uh, I think 0 raised to anything positive or negative. Uh, for negative, should that be uh, uh, an arithmetic issue because 1 over 0 is undefined?
Mm-hmm.
Uh, so in those cases, we'll have to consider that as well. So in these cases, if base is, oh, I'm changing the base here, so I'll create a new. Just put this value result equals 0 and result equals base into base. Okay. So if base is equals 0, then we can return uh, uh, none, or whatever we want to return in this case. Um,
Okay. Yeah,
but
none is
in
fine.
the yeah, um, and the case where the base is 0 and the exponent is 0, I think in that case, should we return uh, none as well, or should that be 1?
That doesn't matter.
Zero?
Technically it's 1, but
Yeah,
we don't need to worry about that. Yeah, that's fine.
yeah. So it's considered on the case. Yeah.
Yeah, that's fine. Yeah. Um, okay. Are there any bugs in the code, or should we? Do you think we should move on to the next part? Any other concerns you have?
Um, yeah. The only thing is like this won't work with any fractions or rational numbers.
That's fine. Yeah, we can assume
This, yeah,
the exponent is integer.
yeah, yeah.
Okay. Um, let's walk through the 2 to the 3 example again, just with the updated
Mhm.
code, see if anything's changed.
Right. Okay. So 2 to the 3, um, we have we do an we loop through the absolute value of the exponent, which is 3. So we multiply. Oh, so I think it should be, there's an issue here. It should be, because this will return the same value every time. It should rather be something like this, so that it actually multiplies by itself every time. Um, and for this case, it'll be 2 into 2 into 2, it will be 8. The exponent is not 0, and it'll return
Can
the
you do that
result.
math again, just so we can confirm it's right? So result is equal to what at the beginning?
Uh, okay, so result is um, the value 2.
Okay.
For each iteration of the loop, it will multiply by itself. Um, oh wait, there's something wrong here. It should be result into base, because it should be, let's say 2 into 2 is 4, it should be 4 times 2, not 4 times 4. Um, and then it should return 8 in this case.
Okay. Let's go through the time and space complexity of this implementation.
Yeah, there's no additional space. We're using constant space, and the time is, and I think the exponent, whatever um, the number of times we have to multiply.
Okay, and how many
So
times do you have to
n.
multiply?
Uh, so if the exponent we assume is n, so it'd be n times.
Okay. So oven time. You're saying oven time, O1 space.
Yeah.
Okay, that makes sense to me. Let's improve this function. Let's improve the time complexity specifically of this function. What are some
Okay.
ideas that you might have for how we can reduce the time complexity here?
Mm, um, Let me think. Mm. So right now, what we're doing is like for each number, we are um, iterating through uh, the how many numbers there are in until the k value. Um, I'm thinking of a way that we can simplify this part.
Mm-hmm.
Um, hmm, um, mm,
Think of a more obvious case first. For example, 2 to the power of 4.
yeah, yeah. When we do 2 to the power of 4, um, I think uh, 2 to the 4 is. So I think 2 to the 4 is similar to um, 4 squared as well, but that still
Yep.
doesn't really. Uh, yeah, so 2 to the power is 16, 4 is 16, and 4 squared is also 16. But I
Okay.
think with that, let me think if there's something that I can use there. Mm, No. Mm, Let me think of anything. Um, I think
Right. So limitation here is that you cannot perform in operations.
right.
Right. I mean, and you don't need to perform in operations. And so, how can you reduce the problem of 2 to the 4
Mhm.
to a problem smaller than 2 to the 3?
Mm. I think reducing 2 to the 4 no smaller than 2 to the 3.
What are some exponent rules if you know them? If you don't know exponent rules, I can give you a couple. But think about how you can
Uh,
reduce these problems to be smaller.
mm, yeah, it's gonna come to me soon. Let me think just a second. Um, could you give me a little hint on the
Yeah,
some of the exponent rules? Because I may not be familiar with something.
yeah. So so the thing is, so if you remember, a to the b times a to the c equals a to the power of b plus c.
Mhm. Okay, B is equals B plus C. Yeah. Mm. Okay. So you're saying that we can break this down into two sub-problems and get a product of their results in
Yeah,
the
there's
case
there's
of
many
2 to
there's many
the
ways to
4.
break down the problem such that the equation is true, but you need to break it down to be smaller than the just trivial reduction of c equals 1. Because what you're doing here is you're saying c equals 1. This is c equals 1 right here,
Hmm.
right? Can you make this
Yeah.
not 1? Because otherwise it's the same thing as linear. So you need to think about how to use this rule to make this not 1.
Mm. Hmm. Um, I think can 2 to the 4, let's just think about this case and maybe I'll have an idea.
Yep.
2 to the 4 could also be uh, 2 to the 2 to the 2 into 2 to the 2. So they have the same base.
Yep.
Um, so in general, I'm thinking every problem, every exponent, we can iterate to until the half of it, and then whatever we get, we multiply it with itself
Mm-hmm.
once more.
Okay. And what's the
Okay,
reason
maybe we
behind
can,
that?
uh, because based on this rule, um, we can break down any power into a sum um, if the base is the same. And the, the way I'm thinking of doing it is like if we have uh, instead of doing the whole n operation, we can try to do n by 2 operations, and because the other half would be the same value as the first half, we could do a product and save some time.
Yep. Okay. That makes sense. We can revisit the math behind that later, but let's go with this approach.
Okay. Yeah, so with this approach, I'll only iterate through the half of the absolute value of the exponents. And in the result, I'll just turn result times itself because I know the other half would be exactly the same as the um, this. Uh,
Okay. And what would be the time complexity improvement on this?
Still be n because, but we'd be saving some operations because we're doing
Yep.
half of the, yeah.
Okay. What if we do it like this instead? Now we do 8. Can you walk me through how 2 to the 8 could be broken down? So we know trivially that
Yeah.
2 to the 8 would take 8 multiplications of 2. That's 8 operations.
Hmm.
Um, can we do less than that? Can we?
Yeah. So with the current thinking that I'm
Yep.
following is like we do 2 to the 4
Okay.
and we multiply 2 to the 4 by itself.
Yes. But how do you multiply? How do you find 2 to the 4?
That will be, that I'm thinking would be iteratively done, but there could be some way that we
Right, but
can.
right, right. But why are you saying it should be iteratively done now? If this was 2 to the 4, you wouldn't have said to do this
Oh yeah,
iteratively.
that could also be broken down into uh, 2 to the 2 and 2 to the 2's. And then, okay, think I'm getting what you're hinting at is we can break it down into further subproblems of just half and half. And at some point, we'll get down to a really simple multiplication. And this could, it looks to me like a recursive approach.
Okay. Yep, that's definitely one way to do it.
Um, but I'm still thinking that approach would, how would we actually save um, some time with it? Um,
I mean, you can go through and count it. How many operations would you need?
mhm. Okay. Um, I'll write another function so that to avoid any fusion.
Yep.
Um, same everything, but um, okay. So if the exponent is 0, turn 1. If the oh, exponent is less than 0, um, I'll do a pod here, but these are like the other cases, and then I'll create a half. Will be uh, calling will be the recursive case. So calling this function by the half of the exponent will be. I can't think of something for exponent when less than 0, but I'll come back to it. Um, be calling the same function. I'll just maybe I'll call something else to avoid calling the same function with the same base and um, the exponent over 2. And then if the uh, should be just uh, in the less than 0 case, it'll just be turn 1 over something. Turn 1 over the um, um, I think this would be a call again to the recursive call, but in this case it'd be uh, would it be the same? No, it'd be still negative, right? The exponent. And or using an absolute. Oh, I have an idea. So if it's negative, we'll make it positive, and because we're doing 1 over, the result would be correctly set. So I'll just do the negative of the value here. Um, and then I have this half, just to return uh, half into half. Let me think. Equal 0 and 0. Keep dividing. Um, is this good? I think. Mm, I'm thinking of something as another thing now, because before the numbers that we tackled with may have some things that we didn't uh, we were expecting, but because in this case we were thinking of fours and eights, but what if it's like a five?
Mm-hmm.
And how would we break that down correctly? Because right now what we're doing is like dividing, and this will just cause some issues, right?
Yep.
Um, because it'll be one more. If I do four, it'll be one more multiplication if it's actually five, then the half strategy. Oh, I can do, maybe I can do something like if the opponent is even, I can do the half-half strategy. And otherwise, I can just do um, the half half multiplied by uh, the base or the base, yeah, and again multiplied by the half. So basically, one more, or not the base. Because I'm thinking in
Mm-hmm.
the case of, let's say, five, if we broke it down into two equal halves, we'll be actually doing 2 to the 4, and because we're rounding
Yep.
down. And I think in that case, at the end, we just do one extra um, multiplication.
Okay.
Does this make sense?
That makes sense. Are you? I mean, do you want to walk through an example, or are you happy with it?
Uh, yeah, I can try to do some examples because I'm not even sure that this will work right now. Okay, so let's do 2 to the 8 like we were doing before. When we enter this function, none of these first two conditions are true. We get to this, we call this function recursively on 4, same base. Keep calling it until the base becomes 0, and we return 1. Or wait, yeah. And then we have exponent mod 2 equals 0. So if the exponent is 0, we have this half value that we calculated recursively, and we multiplied by itself. And then if it's odd, we just do an additional multiplication with the base. Um, I'm thinking now. I think this will work for the case that I'm thinking of, but I don't know if it'll. Let me think if it'll save time.
I mean, you could do. Yeah. I know you wrote 2 to 8 here. You can do like 2 to the. You can do even simpler, like do 2 to the 3, for example. See what
Hmm.
happens in this case, because we don't really need to worry too much about the recursive case, but like I want to see what you think this will actually return.
Okay. 2 to the 3. So you're doing the half of calling 3 over 2 is
Let's start from the
basically,
beginning. Let's start from the beginning. So
yeah,
this line's executed
yeah.
first.
Okay, okay. Yeah, the exponent is 3, so we don't need any of these
Yep.
conditions. We call this, we do over 2,
Okay.
3 by 2. I think rounded down it'll be 1.
Okay.
So we'll be calculating the half at the power of um, 1. So basically, uh, we'll be calling this function to 1,
Okay.
and
Yep.
then again we'll go through another call where we come back here.
Yep.
Now it'll become 2 0.
Okay.
This will return 1,
Okay.
base case,
Yep.
and the half will be 1,
Okay.
and the half is odd. 1 is
The
odd, so we will.
sorry, are we checking if the half is odd or the exponent is odd?
Oh, right, right. So yeah, so the call is with the exponent. The exponent is gonna be. Wait. Um, okay, so let me go back to it. So we are calling with 2 to the 1.
Okay.
In the next call, we're calling 2 to the 0,
Yep.
and exponent is 0. We return 1 for half. The value of half is going to be 1.
Yep.
The exponent is going to be 0. Um, and
The exponent was
oh wait, it
0
was
inside
1
the call. This
inside the call,
exponent
but
is still
outside
1.
it's 1. Yeah,
Yes.
yeah. The exponent here is 1.
Okay.
So 1, we when we reach this condition, we'll be doing 1 mod 2,
Yep.
and then it's not 0, so we'll be doing 1 into 2 into um. Let me think. Yeah. So we'll be doing 2 into 1, which is 2, and returning that. Um, and then going back to the previous case where we get this value of 2 when the half value was 2 in the recursive call. Um, at the end, in the last case, we'll be doing this part of the code at exponent 3, which is odd, which is the outermost call, and we'll have 2 into 2 into 2 in that case.
Okay. Uh, let's talk about the time and space complexity of this function here.
Mm.
So
I know that
walk me through
we
what you're thinking, because there's some recursive cases. So tell me what you're thinking.
yeah. Um, I think the time complexity of this, let me think, because um, we are reducing the the power on each call.
Okay.
Uh, we are halving it.
Yep.
Um,
That's right.
and I think we are probably going to be making log n calls in that case. Um, and if each call is not doing anything else, So
Mm-hmm.
I was thinking you'd be possibly be doing the of log n in terms of time.
Okay. Yep.
Um, but in recursive functions, the thing that's a little hard for me to understand sometimes is the recursive call stack.
Okay.
Um, and I think we're storing values for each call. So I'm gonna assume that we're also storing log n as well. So both the space complexity went up in
Okay.
this case compared to this one.
Okay. Yeah. No, that sounds right to me. Cool. Okay, let's go into another question then. I think that's about wraps up this one. Um, just we're a bit tight on time, so let me see if we
Yeah.
can get a maybe a bit of a one for the right. Okay, I think this one would be appropriate. Okay, so this is a new problem now, right? So I'll dictate this one as well. So
Hmm.
for this problem, I would like you to write me a function called merge intervals.
Hmm.
Okay, the input to this function will be a list of integer pairs. Okay,
Okay.
and then the pair represents the starting and ending inclusive of an interval.
Okay.
Okay, and
So
you
it'll be
are
like tuples, right?
yes,
Like these.
pairs. Yes,
Okay.
that's right. Pairs of integers. That's right. And you are to return a list of pairs that
Hmm.
represents the same intervals if they were merged together, such that there are the minimum number of pairs used to represent the intervals.
Mm. Okay. So I'm imagining, let's say, let me draw like a number line, uh, 5, and then so on until like 9. Let's say in the intervals we have a tuple of 1 to 2. We have one from 2 to 5, and then 5 to 9. So I'll be returning just 1 to 9 because it covers
That's right.
all the. Okay. Okay. And if let's say if there are spaces between let's say it's 1 to 2, and then the other one is 4 to 8. So I'll
Yep,
be returning tuples.
that's right.
Mm. Uh, okay. Um, But am I covering the entire range? Let's say if uh, the the last number that's in the range is like let's say 9 in this case. Uh, if there's, let's say, missing items in that interval, I'm not supposed to have a new tuple for that, right?
That's right. Yeah. So the representation of the merge interval, like the merge interval, should be the same. So they shouldn't add or remove any intervals.
Okay, okay, okay. Hmm. And are these intervals sorted?
No, not necessarily.
Oh, okay. I think that'll be a challenge, is these, because if I have sorted intervals, I could possibly do it fairly easily, where I would take a look at the starting point of one interval and then see uh, until which interval it goes on until, if that makes sense. So I'm thinking that the approach I'm gonna go with, the simpler approach will be to begin by just sorting these intervals. That'll cost some runtime, but I think it'll make my job easier, and maybe we can think of some optimizations later on.
Okay.
So I'll just do so call these. I just say yeah, that's fine because we understand that is. So the arrays of this array of intervals is do array dot sort, I think, and then but how should I sort them by? I could sort them by, because one thing we know about these intervals is like these tuple is like this is the starting index and this is the ending index. So the starting index will always be before the ending index.
Oh, sorry.
Uh,
Can you repeat that? Sorry.
so these tuples,
Yeah.
let's say if, there's a lot of tuples here. Uh, all these tuples, the inside the tuple, the starting index is before the ending index because it represents the line, the like the positive line number, right?
We can assume that.
Okay. So I can probably sort by the first item in the tuple then. So like uh, this. So sort by this value in every range tuple.
Okay.
Um, Let me think. And I have to create a array of merged return array. I'll just call this return array so that I know. Um, And okay, so hmm, I'll loop through each interval. So for I in array, um, I'll have to compare two intervals. Um, Maybe I can start the loop from the second index and store the first index so that I have a previous value to compare against on every iteration. Um, yeah, so I'll just do the starting index in the array, and the loop will begin at the second index onward, so that makes comparisons easier. Um, okay. Um, so the I'll do if I at 0, which is the second starting, like the current value, the starting of the current value is less than the ending of the previous one. So it'll be an array. In Python, I can do something, I think, right? To pop the last one, -1, I think, and then the first value in that tuple. So in the current, I'll do a little bit because this looks weird. Let me think of
Okay.
this just a second. So the what I'm doing here is like I'm iterating through all the tuples in that array. I have the first tuple in the return array already.
Okay.
Um, and what I'm doing is like I'm looking at the starting point of the current tuple in the array and comparing it to the previous item added to the array, and then looking at the ending of that previous item. So if let's say if there is overlap, I would have to merge the previous item with
Mm-hmm.
this item. Um, so it should be less than equals to, so there's overlap here. This is the overlap check. Um, I would just do return array add -1, just like we did before, equals, so it will be a tuple again. The first value will be the same as in the array before. So it just be return array at -1 at 0, because that I'm assuming because it's sorted, so it'll be possibly uh, before this current value every time, or at most the same. And the ending value should be because that's not really sorted. So I can get the bigger one of the two. So
Mm-hmm.
um, so the add -1 at 1. Wait, something is going on. No, wait, here. So and 1, and then the I at 1.
Okay.
Let me think. Is this right? I think so. I could also do a min, but I know because it's sorted, so I don't really need to worry about this left two, that left value in the tuple. So um and in the other case, because if it's greater than this, I at 0 is greater than return it, then that means that there's a gap. I'm assuming. So I just add it to the array. Possibly just add this tuple to the array. What uh, is it? What's the function? Dot push or dot append? Dot append and then put in the I. And then return the return array. Balance. So we have a sorted array. We created a return array with the first tuple in that sorted array. We loop through the remaining tuples. We check if the starting value in the first tuple is less than the ending value in the previous tuple. If it is, then we change the ending value of the previous tuple and forget about the current tuple. And if it's not, we add the new tuple to that array. We return that array. I think this looks right, but the only concern that I have now is like I'm sorting this, and I can't think of any other way to deal with this.
Mm-hmm.
So the runtime would be at least n log n.
Yep.
Does this approach make sense?
Yeah, it makes sense. Yeah. What's the
Okay,
time? What's so your time complexity is what's your time complexity on this one?
I'm thinking n log n.
Okay.
It's
And
the sorting,
yeah. And the
and
space
I can't do
complexity.
better, can I? The space will be n because I'm creating a new array. Um, and that could be at worst the same length as the provided array.
Yeah.
Uh, but the thing is, like, I don't know if there is a better way to do this. There must be. I think. Thinking of the starting array. You need the entire. Yeah, I'm thinking this approach is probably the naive approach. There's something better I'm thinking of.
Why do you think that?
I don't know, because usually in every lead code problem, if I sort something, it's probably usually the worst idea.
Okay.
But I can't think of anything. Yeah, yeah, I'm out of ideas.
Okay. That's fine. I mean, we're about at time for implementation, so let's call it here then, and we'll go into the post discussion.
Okay.
Okay. So, I mean, generally speaking, for these to open up, what do you feel like was good? What do you feel like didn't go so well? What's your assessment of this interview?
I think I think it's something that didn't go well. I'll go begin with that. I
Okay.
think I have some natural discomfort with I said with the dynamic programming, but also with recursion as well. I think that's why I have like even now when I work, I'd never use recursion. I usually even with DFS or BFS, I do it iteratively
Okay.
because I'm just scared of not considering the right things.
Yeah.
And I think that showed here as well because in the first problem, I had no idea um, about the recursive idea. And the second one, I don't know. I still don't know if it's the best idea. Um, Not sure, but that's the only one I could think of. Um, yeah.
Mm-hmm. Okay. I mean, I mean, for the first question, you don't have to do it recursively. You can do it iteratively as well, right?
Yeah, yeah, yep. The thing is, like, even with the ideas that I have done iteratively that are recursive, I had to look at the recursive approach first, and that I cannot come up with myself a lot of the times. I have some issues with it. I think the best way will be to practice or to learn more about recursion.
Yeah. I mean, yeah. There's definitely improvement to be had in terms of like finding the recursive or iterative, doesn't matter to me, obviously, solution.
Hmm.
I think the main thing really comes down to what you're comfortable with, right? Because all
Yeah,
iterative solutions can be written recursively and vice versa, and it's okay to prefer
yeah,
the iterative one. You can prefer that; that's totally cool. But you just have to make sure, no matter what you're doing, you have to be able to do one of them, right? Like that's what it comes down to, right? The interviewer
yeah,
is prepared
yeah,
for both variants, but you have to come up with one of them at least, right? So that's what I would say about
yeah.
that. Now, obviously, the first improvement you suggested was only a factor of two reduction at best,
Hmm.
and that one also wouldn't work if the power wasn't even, which you didn't
Oh,
call it.
yeah, yeah. I didn't consider that at first either. So this one is completely wrong and thinking.
Yeah, that one wouldn't
Yeah,
work.
I think that when you pushed for that idea, initially I was just thinking that won't do anything. It just save time by half. But then I kept thinking about it, and I had that tree in my mind. And then I wrote down the other idea. But that doesn't come to me naturally for some reason. Like thinking of problems in that way.
Yeah, it is a thing, and I will again caution that. I mean, this problem is a math problem, but it's not actually a math problem. Like, you don't need to know
Hmm.
how exponents work to solve this problem correctly. So don't get caught up on that part. But yes,
Yeah, yeah.
it is
I
the case
agree.
that this obviously does get modeled very nicely recursively. It is the like it is a good kind of way to kind of use recursion. Now, more
Right.
specifically about about the real implementation here, the implementation I believe is actually correct, but your initial walkthrough was incorrect. Right, your initial
Oh,
walkthrough of the code, like what the code was returning, what it was doing, was quite incorrect until I pushed you to actually walk through the code line by line. Right, and you
yeah,
can see that
yeah.
you were stumbling on what the exponent was. You got that confused for this case over here.
Yeah, yeah,
So
yeah. Yeah.
right, and so it's one thing to see as a code corrector now, because I mean at the beginning I believed it was correct, but it was a bit shaky. Wasn't too sure. And if I didn't already know all the variants of this problem, I would probably mark you as like questionable slash incorrect on this one, even though it is correct. I think, right, and that's because you don't even believe it's correct when you're walking through it. Right,
Yeah,
so
with these kinds of questions, I can't think of that call stack correctly every time. And initially, I was when I was you were trying to walk because initially I thought maybe this is incorrect because when I was trying to walk through it, I couldn't come to the two to the three answer for myself, so I was just stumbled a bit. And then I saw that that if you think about the returns and the calls, and if you have that track, you can get to the answer correctly.
yeah, so you just gotta be careful about that in terms of being able to walk through your own code. That's a separate
Mhm.
skill, like regardless of whether or not the algorithm is correct or not. Right, like for example, you can have an incorrect implementation, but correctly walk through your incorrect implementation, and that would still be part marks. While if you had an incorrect
Yeah.
implementation, you walked through it incorrectly to reach the correct answer, that would be not correct. That would be double not correct.
Mm.
So just recognize that that's a skill, and if you aren't immediately able to walk through your example, then the interviewer is going to say, oh, they might have just got lucky by writing random stuff down because they just don't understand what's going on.
right. Yeah.
Problems like this you can actually get lucky on by just like there's only so many things you can multiply. It's either correct or not. So it's one of those things
Yeah,
where
and
you have
in
to
this
have
case, it's just
confidence.
itself. Yeah.
Okay, so that's about it for the first question. Are there any things you had like that you're not sure about the first question?
Um, yeah, I think I had a question to you. I don't know, in general, problems that can be broken down into sub-problems. How can I tell? Because usually I can't really tell if a problem needs to be done. Because I think when I gave this answer, like the without the hat, like when I did this, I was thinking like this is probably the best we can do. I couldn't think of anything else. But when you pushed me, then I was forced into looking at other ideas. But just listening to that problem, how should I be like in general? How should I be able to get to that approach?
The main thing is for this problem, you're unless you're really quite exceptional, you are expected to write the naive solution immediately before proceeding.
Mhm.
And as you're writing the
Yeah.
naive solution, you should be thinking about the repetition happening here, which is that this is the same operation that's happening n
Hmm.
times. And if it's
And
the same
times,
operation
yeah.
happening n times, then you should know, okay, well, obviously we can do something about that. Even if it's n
Yeah.
divided by 2, that's something. So when you're writing a loop and you
Right, right.
have this, like that's an automatic signal to say this is probably not necessary, and this is the bottleneck.
Hmm.
That's the sort of signal you should
Okay.
be looking for this kind of problem.
Okay. And for the third one, I don't know if there's a better way to do it. That's what came to me. But yeah.
So let's talk about the second problem then.
Yeah.
So merge intervals. I mean, yeah, so this is correct. This is the right way to do the problem. That's not the hard part. Obviously, I picked the easy one because we're low on time. The main thing here is that's worth talking about is well, there's two things. The first, the main thing is you need to know when a problem or a solution is optimal. You have to know that. The issue
Mm.
with not knowing that is that the interviewer will say, oh, this person doesn't recognize what the invariant is. Like this person doesn't recognize what is going on here. And
Right.
I'll give you a bit more of an academic writing on this one, which is this problem requires you to compare intervals, right?
Hmm.
There's no way to not compare an interval. You have to traverse the intervals, so that's already automatic ON. And then if you have to compare arbitrary intervals, that is automatically in log n. That is just that is a definition of how sorting is in log n essentially.
Mm.
So
Right.
you have to understand the grounded case of if there's no shortcut, if there's no assumption you can make about the order, and you have to
Hmm.
perform arbitrary comparisons, that must be in log n. So there's no way around that, right? And so you have to recognize that because if you don't recognize that, then you're going to be trying to find some other solution, which doesn't exist. So the
Mm.
interviewer is going to
Right.
look at that and say, okay, this person doesn't understand why sorting is in log n. That's a conclusion. Is if you don't understand, how to compare more efficiently, then you also won't understand like the principles of sorting. So this is the main
Hmm.
lesson here. I would say, in general, you should
Yeah.
go through the common algorithms and common kind of strategies, and be
Yeah.
clear with yourself what the base complexity is for these sort of strategies. So
Right.
that's probably a thing we can study on your own later. But yeah, so this one, the main
Yeah.
thing is that it's a bad luck to chase a better solution if you can't recognize the current one as already optimal.
Yeah. For some reason, I have this. Maybe someone has told me about this. Is like a lot of the sorting problems that they do, they use some kind of like that min heap structure, and I got confused thinking that maybe I could save something, but it doesn't seem like because I'm doing all comparisons with all these tuples, so there's no way I can get around that, right? So yeah,
Yes,
makes sense.
and I mean the thing is, like yes, you like the thing about the heap is that like yeah, the heap is still a comparison at the end of the day, right? And
Yeah.
so yes, even though you can technically construct a heap in linear time, you still need to process um,
Hmm.
like you still need to pop all of the items off of the heap, the min heap,
Yeah, yeah,
right? And that's
yeah.
still going to
Because
be
if you're
login.
popping them all off, it'll be n log n. But I was
Yes.
thinking maybe there's some improvement, but there's not. That's something I need to recognize is in this case, I had to do all comparisons. There was no way around it.
Yes,
And
that's right.
yeah,
But yeah, that's the main comment there. The other comment, which is not really too important, is that you did technically like you were sort of making the assumption that the intervals were sorted like within an interval. The first number is a lower one. That technically wasn't given. So if you
yeah,
want to
yeah,
assume that, you need to call it out, which you sort of did, but I just let you assume it because we were low on time. But you would have to
yeah,
you would be
yeah.
expected to call
I
that
was
out.
thinking like the interval would be like from the left to the right, and that's what I said, but I didn't really clarify that too much as well. So I'll note that down as well.
Yeah, technically that's not provided, so you can't know that.
Yeah, yeah, yeah.
Okay, I mean that's all the notes I had. If you have any questions in general, feel free to ask those now.
No, nothing else. Also, I think in this, if there are no intervals, you just return whatever. Yeah, because um, just yeah, because it doesn't have to be okay. Yeah, makes sense. Awesome. Thank
Okay,
you so much for
thank you
doing
for your
this
time.
again.
Take care.
Awesome. Thank you. Bye bye.